A spacecraft flying past a 3-mile wide rock at 30,000 miles per hour had exactly 40 seconds of pure data collection to work with. What it found in that brief window turned out to be one of the most complicated, most revealing asteroid encounters NASA has ever pulled off. Evidence of an ancient collision, a bizarre peanut shape, and something almost nobody expected. Signs that liquid water once existed on this object's parent body billions of years ago. Stick around, because I'm about to walk you through exactly what NASA's Lucy spacecraft found during its flyby of asteroid Donaldjohanson, why this brief encounter revealed so much more than anyone anticipated, and what it's already telling scientists about the earliest history of our solar system. And hit subscribe now, because this channel breaks down real space discoveries without the exaggeration, and Lucy's mission has barely even started. Let's start with what Lucy is actually doing out there, because this asteroid was never even the main event. NASA's Lucy spacecraft launched in October 2021 on a genuinely ambitious 12-year mission, the first ever sent to study the Jupiter Trojan asteroids, two enormous swarms of small bodies sharing Jupiter's orbit around the Sun, one trailing ahead of the planet and one following behind. Lucy is scheduled to fly past 8 different asteroids across its journey, one in the main asteroid belt and 7 Trojans, making it the orbits around the Sun. But on its long journey out to Jupiter, mission planners built in a bonus opportunity, close flybys of 2 smaller asteroids sitting conveniently along the way, treating them as practice runs and genuine scientific opportunities before the main event even begins. The Jupiter Trojans themselves are worth understanding a bit better, since they're the entire reason this mission exists in the first place. These asteroids sit trapped in 2 stable gravitational pockets, created by the combined pull of the Sun and Jupiter, one cluster leading Jupiter's orbit by about 60 degrees, the other trailing behind by roughly the same angle. Because objects caught in these stable positions tend to stay there for extraordinarily long periods, scientists believe the Trojans represent genuinely pristine leftover material from the earliest days of solar system formation, largely undisturbed for more than 4 billion years. Studying them up close offers a genuine window into the raw building blocks that existed before the planets fully formed, which is exactly why NASA committed to a 12-year mission just to reach and study them directly, something no previous spacecraft had ever attempted. If you're the kind of person who wants space discoveries explained clearly instead of buried in jargon, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. The first of those bonus targets was an asteroid called Dinkinesh, and Lucy's November 2023 flyby immediately delivered a genuine surprise. When the science team downloaded the spacecraft's imagery, they discovered Dinkinesh wasn't traveling alone. It had its own small satellite, making it a binary asteroid system nobody had known about beforehand. That satellite later received an official name, Selam, and further the R analysis revealed something even stranger. Selam itself turned out to be what's called a contact binary, essentially 2 separate smaller objects that had gently come together and stuck, orbiting Dinkinesh as if they were one single moon. That early discovery set the tone for what Lucy's entire bonus asteroid campaign would end up revealing. Genuinely surprising complexity hiding inside objects that, from a distance, looked like nothing more than simple, unremarkable rocks. The name Dinkinesh itself carries real meaning tied to the mission's broader inspiration. In Amharic, the Ethiopian language, Dinkinesh means "you are marvelous," and it happens to be the same name Ethiopians use for the original Lucy fossil. The spacecraft itself is named after. Mission scientists watching the encounter unfold in real time captured the moment I first spotted the satellite rising into view in Lucy's imagery, taken within a minute of closest approach from a distance of roughly 270 miles. And by all accounts, the asteroid genuinely lived up to its marvelous name that day. Nobody on the science team had gone into that flyby expecting to find a moon at all, let alone a moon that turned out to be its own separate binary system. If you found this as fascinating as I did while researching it, drop a comment letting me know, because it genuinely helps me figure out what other space stories are worth covering next. The second bonus target was Donaldjohanson, named after the paleontologist who discovered the famous Lucy hominin fossil in Ethiopia 50 years ago, the same fossil that inspired the spacecraft by its own name in the first place. On April 20th, 2025, Lucy flew within just 600 miles of this asteroid, closing in at roughly 30,000 miles per hour, a speed and precision that required an extraordinary amount of navigational accuracy to pull off successfully. The spacecraft had to shield its sensitive instruments from intense sunlight during the encounter, and mission controllers actually had it stop tracking the asteroid a full 40 seconds before closest approach, specifically to protect its cameras from potential damage during the fastest, closest part of the pass. Achieving that level of navigational precision, hitting an exact target distance while moving at nearly 9 miles per second, represents a genuinely difficult engineering challenge on its own, entirely separate from the science the encounter eventually produced. Mission navigators know the positions of both Lucy and the asteroid with extraordinary accuracy well in advance, but translating that knowledge into a spacecraft trajectory that actually delivers the exact desired flyby distance, close enough to capture meaningful surface detail, but not so close that the fast relative motion blurs every image beyond usability, requires an enormous amount of careful advanced planning. The 600-mile target distance for Donaldjohanson was deliberately chosen to thread exactly that needle, close enough to reveal genuine surface features, distant enough to keep the resulting images sharp despite the spacecraft's tremendous closing speed. What came back from that brief window genuinely surprised the science team. The very first images revealed Donaldjohanson wasn't a simple, single-rounded rock at all. It was an elongated contact binary, 2 distinct lobes connected by an unusually narrow, pinched neck, giving the whole object a genuinely peculiar peanut-like silhouette. Hal Levison, the mission's principal investigator at the Southwest Research Institute, described the asteroid's geology as strikingly complicated, adding that studying its complex structures in detail would reveal important information about the building blocks and collision processes that shaped the early solar system. Follow-up analysis, published in the journal Science in 2026, went considerably deeper than those first dramatic images suggested. Researchers determined Donaldjohanson formed roughly 155 million years ago, when a larger parent asteroid was shattered apart in a violent collision. The fragments produced by that impact gradually came back together under their own weak gravity, eventually forming the strange 2-lobed object Lucy actually photographed. That reassembly process wasn't quick either. Scientists studying the asteroid's structure believe it took a genuinely extended period for these fragments to settle into their current, gently touching configuration, a slow-motion process playing out across a scale of time that's genuinely difficult to picture. Here's where the story gets even more interesting. As sunlight has continued striking the asteroid's surface unevenly across the millions of years since that reassembly, it has steadily and measurably altered the object's rotation through a subtle process astronomers call the Yorp effect, short for Yarkovsky-O'Keefe-Radzievsky-Paddock. Essentially, sunlight absorbed and re-emitted as heat from an irregularly shaped surface creates a tiny continuous torque, gradually speeding up or slowing down an asteroid's spin over enormous timescales. For an object shaped as unusually as Donaldjohanson, with 2 distinct lobes joined by a narrow neck, that effect has apparently been significant enough to leave the asteroid in its current state, described by researchers as wobbling, tumbling slightly rather than spinning around a single clean axis, the way a more symmetrical object typically would. The Yorp effect itself might sound like a minor, almost negligible force, and on any short human timescale, it genuinely is. The amount of thrust generated by unevenly re-emitted heat from a small asteroid's surface is almost immeasurably tiny compared to forces we experience in everyday life. But given enough time, millions of years in this case, even a genuinely microscopic continuous force can meaningfully reshape how an object spins through space. Scientists have documented this same effect altering the rotation rates of numerous other small asteroids throughout the solar system, and Donaldjohanson's particular case offers an especially clear example, since it's unusual. Elongated, 2-lobed shape makes it considerably more susceptible to this kind of gradual reshaping than a simpler, more spherical object would be. That susceptibility is part of why researchers found the asteroid's current wobbling rotation state so scientifically informative, offering a genuine window into how these subtle, long-term forces actually accumulate and manifest over cosmic timescales. Then came the detail that genuinely caught researchers off guard. Buried within the data Lucy gathered during that brief flyby, scientists found evidence that liquid water briefly existed on Donaldjohanson's parent body, long before the collision that eventually shattered it apart and created the asteroid Lucy actually photographed. Finding evidence of past liquid water on a small, otherwise unremarkable main belt asteroid is genuinely significant, since water plays a central role in current scientific thinking about how the raw ingredients for life first became available and distributed throughout the early solar system. An asteroid this size preserving evidence of ancient liquid water offers researchers a genuine physical clue about conditions that existed on its much larger parent body before that larger body was destroyed in the same collision that eventually produced the fragments now forming Donaldjohanson itself. This finding connects to a broader ongoing scientific effort to understand exactly how water and other essential ingredients for life spread throughout the early solar system, well beyond just this one asteroid. Similar water-related evidence has also emerged from other recent asteroid sample return missions, including NASA's OSIRIS-REx mission, which returned physical samples from the asteroid Bennu that were later found to contain essential sugars like ribose and glucose, molecules directly involved in forming RNA. While no traces of life itself have ever been found in any of these samples, discoveries like this consistently reinforce the idea that small, seemingly unremarkable asteroids scattered throughout the main belt may have played a genuinely significant role in delivering both water and organic building blocks to the early inner solar system, potentially including the young Earth itself, billions of years before life as we know it ever emerged here. It's worth appreciating just how much information Lucy managed to extract from an encounter that lasted only a matter of minutes. The spacecraft's primary imaging instrument, called LLORI, short for Lucy Long-Range Reconnaissance Imager, captured a rapid sequence of high-resolution black and white photographs as Lucy closed in from an initial separation of more than 58,000 miles down to its closest approach distance of just 600 miles. From that sequence of images alone, combined with additional spectral and thermal data gathered by Lucy's other instruments, researchers were able to reconstruct not just the asteroid's shape, but its formation history, its internal structure, its ongoing rotational evolution, and physical evidence pointing toward ancient liquid water. An extraordinary amount of scientific information to extract from a target the spacecraft only ever intended as a bonus opportunity along the way to its real mission. That's really the broader point mission scientists have emphasized about this entire encounter. Donaldjohanson was never Lucy's primary target. It was essentially a rehearsal, a chance to test the spacecraft's instruments, its navigation systems, and its data collection. Procedures on a real object before Lucy ever reaches the considerably more scientifically important Trojan asteroids waiting near Jupiter. According to researchers involved with the mission, the results from Donaldjohanson, while genuinely valuable in their own right, primarily demonstrate just how much information Lucy will likely be able to gather once it finally reaches the Trojan clouds, a region of space no spacecraft has ever visited before at all. Lucy's journey isn't finished revealing surprises either, even along the way to its main destination. In September 2025, as the interstellar comet 3I Atlas passed through the inner solar system, Lucy happened to be well positioned to observe it as well, its LLORI imager capturing a series of photographs over several days in mid-September as the comet moved toward Mars, even though Lucy itself was still 240 million miles away from the comet at the time, well beyond Mars's own orbit. That kind of opportunistic science, using an instrument built for one specific mission to gather valuable data on a completely unrelated, genuinely rare object passing through the same general region of space, has become something of a recurring theme throughout Lucy's journey so far. Looking ahead, Lucy's actual primary mission is still to come. The spacecraft is scheduled to TEO begin its main sequence of Trojan asteroid encounters, starting with a target called Eurybates in 2027, an asteroid that Hubble Space Telescope observations had already revealed carries its own small satellite, discovered years before Lucy would ever actually arrive to study it directly. Mission. Scientists have already begun preparing for that encounter, instructing the spacecraft to start turning its cameras toward its future targets, even while they remain nothing more than faint pinpricks of light from hundreds of millions of miles away, gradually fine-tuning camera settings well in advance of the actual close approach. That Eurybates satellite discovery followed its own genuinely interesting path to confirmation. Researchers first spotted hints of the small moon buried in archival Hubble images, captured across September 2018, December 2019, and January 2020, long before anyone specifically knew to look for it. According to Hal Levison, the newly discovered satellite proved to be more than 6,000 times fainter than Eurybates itself, implying a diameter smaller than 1 kilometer, making it, if that estimate holds up once Lucy actually arrives to study it directly, among the smallest asteroids the mission will ever visit. Confirming that kind of extraordinarily faint signal required combining multiple separate observations taken years apart, exactly the sort of patient Methodica L work that keeps revealing genuine surprises about targets astronomers assumed they already understood reasonably well. So what does all of this actually add up to? The spacecraft, on its way to study a completely different population of asteroids near Jupiter, made a brief 40-second close pass of a 3-mile-wide practice target and came away with evidence of an ancient, violent collision, a genuinely strange peanut-shaped structure still slowly reshaping itself under the influence of sunlight, and physical proof that liquid water once existed somewhere in this object's history, long before it was ever shattered apart. That's an extraordinary amount of science to extract from what mission planners always described as simply a bonus opportunity, and it offers a genuine preview of what Lucy is now expected to reveal once it finally reaches the Trojan asteroids. A part of the solar system no spacecraft has ever explored up close before. There's something genuinely fitting about how much this single practice flyby ended up revealing. Lucy was never expected to make Donaldjohanson its defining scientific achievement, and mission scientists have been consistently clear that the Trojan asteroids remain the true heart of this entire 12-year journey. But if a target chosen essentially as a warm-up exercise can produce evidence of ancient collisions, ongoing rotational evolution, and traces of billion-year-old liquid water, all from a flyby lasting mere minutes, it becomes genuinely difficult not to wonder just how much more Lucy stands to reveal once it finally reaches asteroids that have never been visited by any spacecraft in human history at all. If space discovery stories like this one, grounded in real published research from science and NASA's own mission teams, are what you want more of, subscribe to this channel and turn on notifications, because Lucy's primary mission is only just beginning, and there's a real chance the next encounter reveals something even more surprising than this one did. Thanks for watching, and I'll see you in the next one.